In this video, we're going to continue our study of trig substitution. Now, we've already covered the basics of trig substitution in the previous video, but basically, in summary, it was this, is we were trying to integrate certain expressions that have radicals in them, and it was very difficult. So what we do is we substitute these trig expressions in for the radicals temporarily because it makes the integration easier to do. Now, there's a lot more details, obviously, to it than that we worked through in the last video, but I don't think we're going to repeat most of that here. Now, the thing about trig substitution, however, is that there's three different types of substitutions that you do depending on what type of radical you have in your integral. The first type has already been covered. We're not going to talk about this type. If your integral has a square root of a squared minus u squared somewhere in it, then there's a particular type of substitution that you do for this type of radical. But in this video, we're going to move on to the second type. This is the one we're going to look at, the square root of a squared plus u squared. There was a third type as well, and we'll cover that in the next video, but these last two will be significantly shorter than the first video. All right, so let's assume that our integral does in fact have somebody who looks like this. It could be something as simple as, the square root of, 25 plus x squared, for instance. If you would have an integral with somebody like this in it, it very well may be trig substitution. All right, so you remember our idea in the last video was to write this guy as one of the sides of a right triangle, and then using the Pythagorean theorem, we can figure out what the other two sides should appropriately be. Now, let's think about this one, though. In the last video, there was a minus, but now there's a plus. When there was a minus, it made pretty good sense to put this guy on this leg because you had a squared minus u squared, and then this side could be a u, and this side would be an a, and the Pythagorean theorem would work. It would work. But let me ask you a question. If that minus was in fact a plus, would this actually work out too well? I don't think it would, because since this is a plus, then there's no way that you can create a negative term over here to subtract, because this side would be squared when you do the Pythagorean theorem. So if we shouldn't put this guy on this edge right here, where would he be more appropriately put? Well, if you think about it, I think you would agree with me that I think we should put this guy on the hypotenuse for this time. We'll have the square root of a squared plus u squared on the hypotenuse, and then what would that lead us to believe that this leg and this leg would be in order that the Pythagorean theorem would still hold? Hopefully you would say a and u, right? A and u. So we have this relationship here, and sure enough, a squared plus u squared equals the square root of a squared plus u squared squared, because then the square root and the square would cancel with one another. So same idea. It's not drastically different. We're just putting these things in a different place because it's this type of radical as opposed to another type of radical. All right, but from here we're going to proceed in the same fashion. We'll call this angle theta. Now, I would love a trig relationship that relates theta with u. Now, you could use the opposite edge in a tangent relationship. Tangent of theta equals u over a, or a sine relationship, u over the radical. Which would we prefer? I think I'm going to go with the tangent relationship just because it's easier, right? Tan of theta would be u over a. I would rather have u with a constant as opposed to u with a messy radical. But notice you can rewrite this guy as u equals a times tan theta. All right, let's put a box around that. That's going to be very important going forward. This is our substitution that we use for u if your radical has a plus, a squared plus u squared. Now, if your radical integral has a radical in it, then we also need a substitution for that radical term. So let's write one down for the radical term. For this one, we want to incorporate theta with the radical. So what uses the hypotenuse? Well, cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. I think I'm going to go with the cosine relationship. Cosine of theta would be a over over the square root of a squared plus u squared. And the reason I chose cosine over sine is this relates to the radical with a simple constant as opposed to the radical with a variable expression. It's just simpler, it's just easier. But notice if you rewrote this guy, if you move the radical up here to the right hand side, you would have the square root of a squared plus u squared equals to, and then we would also have to divide the cosine over to the right. So you could say a divided by cosine theta, but instead of saying divided by cosine, remember that's the same thing as times secant of theta, times secant of theta. So let's put boxes around these two guys. These are the ones we've been looking for, this guy and this guy. So in short, when you have a radical in your integral that has a squared plus u squared, then these will be the two substitutions you'll make. Now, one last thing I'll mention before I let you go is that remember, I said in the last video that most textbooks actually write this down as a, if you have this, then you make this substitution. And if you have this, then you make this substitution. And it's all correct. There's nothing incorrect about it. But just from my experience, it's difficult to memorize that much stuff. So what I typically do is just kind of do these on the fly. If I have an integral that has somebody like this, then I'll literally make up my own right triangle right there on the page. I'll put him on the hypotenuse. I'll figure out what A is. I'll figure out what U is. And then I'll write my relationships. And that way you can just kind of do it on the fly and lessen the things that you have to memorize. So anyway, hopefully that helps you with understanding how to handle the second type of trig substitution. We still have one more to go that we'll cover in the next video, but hopefully at least this helps you make good progress towards understanding these three different types of trig substitutions.